Hello. Hey, hi everyone. So my name is Thanh from Vietnam, and we have Uyen. Yeah. So we have Uyen as our one of our member of cryptography research team. Going to Today we're going to present about like a critical proof attack on the zk EVM. So it's a zero knowledge proof for the layer 2 solutions for to scale like like EVM layer of, let's say, Ethereum on blockchain, for example. Okay, let I move next. So basically, we are from Verichains, so it's a firm that from traditional security, and also we are providing the Web3 blockchain security audit, and we have also do a lot of cryptography, crypto analysis, red teaming, and investigation. So basically, we are the firm that helping in most of the largest, like Web3 or blockchain hack happening globally. So here we have like BNB brick hack with $600 million, or Ronin hack with $615 million. So we actually are working with those vendors that are helping to find out the root cause, what is the issue, and how to fix it, and so on. And we also discover a lot of critical vulnerability in a lot of layer 1, layer 2 blockchains. Also, last year we presented a critical private key, extraction attack on a lot of multi-party solution, right, based on the threshold signature scheme that we use very widely in, like the multi-party wallet, like in exchange, or some custody assets that are handling the large amount of money. And we also have found a lot of issue around like zero knowledge proof, which is also the talk today, that we found the issue last years, and it takes the vendor like quite a while to fix that and actually implement that on the mainnet. So that's why today we present. We're also working on traditional security solution, something very special like e-passport, EID, smart card implementation, cryptography part around that. Like I just shared, right? So we behind those, we support a lot of vendors on helping the issue, especially around like the crypto hack. There's a few things that here is like when this hack happen, right? So it's sometimes that depending on the nature of the issue, right? Sometimes you take a long time to really understanding why it happened, what's the problem relies under the protocol, and how to fix it as fast as possible. This is what we presented last year on the multi-party wallet that affected, billions of dollars. So around all of those custody assets, utilize the MPC technology is handling like billions of dollars, right, assets in cryptocurrency. Let's skip this. So today talk is about like the proof for the attack on the zkEVM. So basically today we're going to along with the talk, discuss about the issue, how we find it, how we exploit that, as well as we have the demonstration on two basically a scenario. One is to free own of crypto assets on chains, and the second is to steal the money, right, from the network. So you know that, right? In terms of a lot of different cryptography, traditional security, we have been using a lot of cryptography to secure a lot of different protocols. And it takes years, right, to make the protocol proven to be secure and being used widely. But then for the blockchain, right? So the thing is like moving very fast, and it's tend to adopt a lot of new way or new technology or new cryptography algorithm to be able to make it more, like scalable, to make it more usable and more applications on the blockchain. So that's the reason why it's actually potentially there's a huge issue around that because the protocol is new and not proven yet. So that's exactly where we, how we actually align with our research on the offensive research on this kind of thing. So we looking at the new technology that handling billions or hundred millions of dollars in cryptocurrency that utilizing, like the protocol. I mean, like MPC, for example, it's not a new, right? It's not a new protocol. It's a long time protocol. It's a very old protocol, and it's been regulations from time to time. But then it's actually when the blockchain and own of the, let's say the private key, right? You lose the private key, you own the money. How you can be able to split the key into multiple party and able to make the transaction that require a number of different signature and different party that sign the transaction because it might happen. So it's how to protect and how to actually prevent the issue of like losing one of the single key and you lose all the money, right? But at the same time, right, the technology itself also going to, because it's not proven to be secure yet, and so along the way, there's also the way that what happens if there's one by access to just one single party and but able to retrieve the whole private key, right? So that exactly is how we present our attack last years on the attack that we are able to extract the private key out from just a single party. Okay. So for the next part, I will let Uyen to continue to explain about like the our zkEVM bug that we found on Polygon implemented layer 2 implementations, and also the demonstration of the attack.
Okay. Thanks, Dan, for a great overview. So next, I will be in charge of explaining the technical details of the research. So in order to understand the vulnerability, I will give you all the layers step by step, beginning with the big pictures of the layer 2 network of zero knowledge. So next is the host of the layer 2 network, that is the zkEVM component. And the stock protocol is the underlying proving protocol used in the zkEVM. And the next layer is the file polynomial commitment scheme, which is the security of the stock protocol relies heavily on this file commitment scheme. And the lowest layer is the Merkle commitment scheme, which is where the file polynomial commitment scheme was relied on. So first, let's take a look at the layer 2 roll-up solutions of the Polygon zkEVM. So I want to give you the overview of the life cycle transaction. So first, when the user have signed and sent the transactions to the network, then the transaction is gathered in the pool right here, and then it's being verified and being ordered into a batch by the joystick sequencer. And after that, the sequencer sends broadcast the batches to all the layer 2 nodes. It also commit the batch to the layer 1 network Ethereum. At this point, the batch does not have a validity proof yet. So this is when the joystick aggregator comes in place. So the joystick aggregator together with the prover component will carry the proof to prove the correctness of several batches at a time. So the joystick aggregator will run the proving protocols to prove the correct executions of these transactions. So with the proof forgery attack, the aggregator can not know the valid batches or do not require to know the valid transactions to update the state. That is extremely dangerous. So we have known that only the joystick aggregator can submit the proof to the layer 1 to update the state. So in this slide, there are several information corresponding to the proof. That is the start number of the patch, the end number of the patch to be proven, the old state root corresponding to the current before the proof is verified, and the new state root is the value after the proof have successfully verified by the Polygon zkEVM smart contract. So let's take a look at the host of the layer 2 network, that is the zkEVM component. So you can think of the zkEVM as the special VM that take the old state together with the transactions. The zkEVM executes it and output the new state. However, it also output a proof of execution that is states for the zkEVM have correctly execute the transaction and compute the new state. So what is each component of the zkEVM? So first component is the zkEVM, which is stand for Zero Knowledge Ethereum Machine. So these stand for transaction execution logic, which is implemented in assembly language associated with the second component, the zkEVM. Next, the second component is the zkEVM. You can think of the zkEVM as a type of VM that the correctness of the computation on this VM can be proved, and it is implemented in the PIL language, which is the third component. So the PIL stands for Polynomial Identity Language, and it describes the hardware parts of the zkEVM, including the register, the supported exclusion, as well as several polynomial constraints. And the final things, the most important things, that is the stock proof system. So this proofing system is used to prove and verify chase polynomial satisfying the constraint that defined in the PIL file. So in order to break the layer 2 network, we have to break the stock protocol here. So next is the detail of the stock protocol. So stock has 6 rounds in total. For the first 4 rounds, the prover and verifier mainly committed polynomial to each other. And at the round 5 and round 6, the prover have to provide the verifier his polynomial evaluations at the point random C. And together with the proof of correctness of these evaluations. So the securities of the stock protocol rely heavily on the security of the flaw protocol. So if we can provide a proof that can bypass the second conditions of the verifier algorithm, we can break the stock protocol. So the verifier will accept the root, the proof, if the first condition is the Q polynomial equations as C must equal to the constraint as C over the vanishing polynomial as C. If you are a big fan of zero knowledge protocol, I think you may have known this equation. And the second condition is that the polynomial evaluation proof is correct by means of the flaw protocol. So the security, as I said before, of flaw polynomial commitment scheme relies heavily on the security of Merkle commitment scheme. So if we can break the Merkle commitment scheme, then the whole ESTAR, zkEVM, the layer 2 network also being vulnerable. So next is the Merkle commitment scheme. You can think of the Merkle commitment scheme is a scheme to commit and review. The prover will have to commit the polynomial without telling his coefficients of the polynomial, and later the verifier have to query the prover to have some evaluations at several points. And the prover have to review the evaluations together with the Merkle proof for that evaluations. The security relies on how many times the verifier query the prover, also the randomness of the challenge. So let's take a look at how Merkle root being computed. So the first message of the prover is the MTR, which stands for Merkle root. If the prover wants to commit the polynomial f1 to fn, first the prover have to build a table contains evaluations of f1 to fn at each point from the evaluation domain H. And for example, each line, each row of the table contains the evaluations at the point H. The first line is the evaluations at H1. The second row contains the evaluation at H2, and so on. In order to compute the Merkle root, each row is going through a leaf hashing function to output a leaf hash, and each pair of the leaf hash is hashed together in a long way to provide the final Merkle root. So if the leaf hashing function is variable, in this case is variable leaf hashing function provide the hacker to perform the hash collision. So for example, at first the prover wants to commit the polynomial f1 to fn at O0, and then later he will maliciously reveal not the 0, but a other value that is x, y, and z, for example. So he has to compute the leaf hash of O0 must equal to the leaf hash of x, y, and z. So that is how we can break the commit and reveal Merkle commitment scheme. Next is the star optimizations, where the variability star. So we have seen how to generate a star proof, which is we are at this point. So the Polygon team have designed a scheme to optimize the proof size, also the verification time of each star. So after we got the star proof, the verifier algorithm of each star is transferred into a snap circuit. This is right here. And then the star proof together with the peer constraint is also converted into the secret witness that is satisfy the snap circuits that verify the validity of the star proof, and run the snap proofing algorithm and output the snap proof. So the snap verifier is much more easier to implement it and have constant time to verify in the layer 1 network. So next, why we have to turn the star protocol into snap protocol? So we know that the star stands for scalable transparent argument of knowledge. So it's focused on the scalability of the computation, so it can be used to prove the correctness of extremely large and complex computation, while the proof size of the star is considerably bigger than the snap. And the snap stands for the succinct non-interactive argument of knowledge, which is considered more efficient in terms of proof size and verification time. So when we combine the star proving algorithm with the verification algorithm of snap, we have a new algorithm to prove have the efficiency on both proving and verification. And this slide also the start optimizations. In reality, there's a lot of phase to reach the start to snap. At these first three stages, you don't have to understand these stages to understand the bug. In short, these stages to use to verify the start proof and combine and compress this proof into one recursive to proof. In the final stage, the proof from the aggregation stage is also being verified and but in an order finite field, that is the f of q, where q is the prime number tied to a pairing-friendly elliptic curve that is used by the snap algorithm flaw. After we got the red proof right here, the output of the final state is being verified by the arithmetic circuit of the snap algorithm and output a FF-long proof. So in short, you can think of if we have this red proof, that means we have each proof corresponding to each byte, and we can continue to the final state, that is the snap state. So with the proof forgery attack, we don't have to know each proof right here, but we also can forge the proof and continue to the final state, that is the snap stage. So that is how we can break the zkEVM. From this is the vulnerability details about the incompatibilities between the fields of start and snap. So we have seen that in order to optimize the start protocol, we have to combine the proving algorithm of start with the verification start implemented in the snap algorithm. However, we have to work with the elements from f of PO to the power of 3, which is 192 bit entropy of element from start. However, the element from the snap circuit is over the fields of Q, which is 254 bit entropy. So this incompatibilities create the verbal to break the whole system. So after we have audited the whole protocol, we found two vulnerabilities in recursive F subprocess, which is the phase right before the snap stage. The first vulnerable is on the Merkle-Leaf hashing function, which called the hash collisions to maliciously reveal at another point. And the second is the mun and add gate. So for the first vulnerability, that is the linear hash function. You can think of the input of the linear hash is a tuple of 3 elements, x, y, and z. That is has 64 bits each. So these elements being combined to 192 bits by using the sum and shift left. For example, x, y, z will return to a leaf corresponding to the x plus 2 to the power 64, y plus 2 to the power of 128 z. So this function is called the hash collision of two different leaf values that will have the same leaf hash when being input to this linear hash. At first sight, we thought that by using this vulnerability is enough to break the system. However, there are also constraints on the input size. So by using the second variable functions, we can break the system. So the second function is about mundane add operation. So this function takes three input A, B, and C, and output a result that is A multiplied with B plus C. So this like right here is the stand for the products of A and B. Then before being modulo deductions by modulo 3, modulo P, the product being added with the input C. So at this point, after being added B multiplied with A multiplied with B, the product is roughly 128 bits inside. So when being added with C, the C here has more size than it needs. So by using the two witnesses, we can track the lowest layer, that is the Merkle commitment scheme. So if you want to maliciously commit the polynomial, first is O0 and later will maliciously reveal to be X, Y, and Z, we have to solve for triple of a system of equation on three variables. The first equation is corresponding to the mundane add function. That is A, B, C must be equal to X, Y, and Z modulo P. So A, B, C in this case acts the same as X, Y, and Z when going to the mundane add function. And for the second equation, that is A plus 2 to the power of 64B plus 2 to the power of 128C must be equal to 0 modulo Q, is corresponding to the leaf hashing function. So A, B, and C here acts the same as O0, a tuple of 30 when going to the leaf hashing function. So after these A, B, C, and 0, 0, 0 go to the leaf hashing function, it output the same hash value. So the leaf hash won't change, lead to the Merkle roots won't change, and we can maliciously review at any value we want. So let's combine these two equations into one. That is equation right here. So we have equations for three unknowns. By using the lattice reductions, we will have the solution. Each have roughly 85 bits. However, there is a constraint right here for the multiply and add. The output of these functions must less than 80 bits. So if each alpha, beta, and gamma have 89 bits after the lattice reduction, so it's not satisfy this constraint. So we have to maliciously reveal at two positions, not one. So this is the final strategy to fork a stock proof. So from the first fora, we will commit all polynomials at 0 because we don't have the correct execution, so just commit it at 0. At round 5, we will deduce a tuple X, Y, and Z corresponding to the equations of Q at C. And then we will maliciously open Q1 and Q2 at C as X1, Y1, Z1, and X2, Y2, and Z2, such that we have the relations Q1 plus X2 power of N Q2 must be equal to the Q. And other evaluations for the committed polynomial from round 1 to round 4 will be as the tuple of 3, 0. At round 6, we will run the file protocol as normal. However, in the file query phase, we will review the evaluations of Q1 and Q2 as A1, B1, C1, and A2, B2, C2. So we have several relations corresponding to trail unknowns. That is the system of file relation here. So we have the first equation stand for Q1 at C plus C to the power of n, Q2 at C must equal to Q at C. For the second and the third equation, that is ABC equal to the XY and Z modulo P, that is corresponding to the vulnerable mundane add function. For the fourth and fifth relations, we have a plus blah 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 blah. That is corresponding to the variable leaf hashing function. So by using the lattice reductions to find small solutions for modular linear equations, we have such small solutions for satisfying the 80-bit constraint I have mentioned before. So when we have got the valid stock proof, we can continue to the proof recursion step, that is the snark phase, and got the final zkEVM proof. So the zkEVM proof at the final stage is FF-long proof. So it contains several random numbers and it tells nothing about the technical, strategy of the attacker. So the impact of the proof forgery attack depends on how the zkEVM is used. So in this case, the attacker can forge a valid proof for any computations, and the attacker can change the state to an arbitrary value so that the attacker can steal the funds from the network or freeze the network because of the malicious state cannot change to any further value. And the most important thing is that the zero proof it also contains potential zero knowledge hack. So the hacking technique is completely hidden by the zero knowledge nature of the argument system. So it tells nothing about how the attacker can forge a proof. For the fixes, the fix is very simple. For the first variable functions, we have to check that all the input to the recursive f must belong to the prime p. And for the variable multiply then add function, we have to separate the two operations into two different functions, that is multiplications and addition. Next is the live demo, of course, the most interesting part. So I will demonstrate two scenarios that the attacker can use the proof forgery attack. The first is to freeze the whole network. So we will use the fork proof to change the state of the forked Ethereum at this block height. And we will change the state root to O0. And then if you want to withdraw your money, you have to find a Merkle proof corresponding to the root of O0 to withdraw. So in this case, the user unable to withdraw money. Here's the input to the verify function. So you can see here the old state root is some value. And the new state root and new local exit root is changed to O0 here. And this is when we execute the POC, the root after we have submit the proof is O0. We will have live demo for this scenario later. For the scenario 2, we will use the proof forgery attack to steal funds from the Polygon zkEVM bridge. So also we have to use the forked Ethereum mainnet at this block height. And this strategy is to change the local exit root to a value such that only the attacker knows how to withdraw the money. So the attacker can drain all the funds from the file by and sends to his chosen address. Let's skip this and switch to the live demo. So I will combine the two scenarios in one POC. For the hard config, I will fork the Ethereum mainnet at this block height. And this input corresponding to the fork proof. So the current state root is 3F86, blah, blah, blah. And the new state root is 00, as you can see here. This is the fork proof, which is a FF long proof. As you can see that everything looks random and this tells nothing about how the hacker can fork the proof. So let's run the script. Okay. So first we will fork the Ethereum network. Next, only the trusted aggregator can submit the proof. So I assign the signer to be the trusted aggregator. I bring the current state root, that is the TF86 as before. Submit the fork proof and bring the after we have submitted the proof that the state root has changed to 00. Bring the current fund, that is over 9,000, and we request the withdraw money, and bring the funds after we have withdraw all the money. So after we have submit the proof and withdraw the money, the funds from the vow is only 4 tokens. And this is the end of the demonstration for the two scenario. Let's back to Han.
So basically, what we just showing in the demo is the actual payload that we share with Polygon team last year's, so basically the demonstration actually we take from the mainnet of the Ethereum and send to them. And if you look into a slide that on this slide, you will see that is the reason why it's completely hidden is because it's zero knowledge proof, right? It's supposed to be zero knowledge. So even when we do the hack, even when we share with the team on the POC, they will not really know what exactly happened and where is the probability of our and how we do it. Like until we actually, and even we send them the codes, right? Until we share with them the full paper, but we write up in detail on how it works and where the probability lie, then it's how. And the beauty of this is when you do it, no one knows exactly how you do it, right? Because it's the zk technology by itself is supposed to be right to maintain the privacy and the information. And we work with them for many months to fix the issue in the mainnet, as well as many others like project that actually fork from the code base to use it. And as well, I mean, we got a big bounty from them as well, like thanks to the Polygon team. And after that, we are now their partner on securing all of these technology. So for the conclusion, right, I think that right now we're also working on something else. But if you look into this way, right? So MPC, when we start looking in all of the multi-party, the threats, the sharing threshold key and so on, right? Is about 2 years ago, right? When we found out the attack, it took us about 9 months to work with all of the vendors, and eventually we released the research on August last year, right? When we're actually working for all of issue on October on 2022. So it's basically about 10 months. For the zk, for this zkEVM bug, I think we found it last year in Q3. We report to Polygon team, and actually only until like last month we start like now about the issue, right? And today is the first time actually we talk in detail about the issue. And also, if you look in the way that we exploit all of these bugs, it's not single bug, right? It's a lot of time we need to change multiple issues from the protocol, from the math, from the cryptography component, all together in order to achieve like the final result, basically just steal money, right? Or in the MPC, the result is we're able to retrieve, right, or extract the private key, which is eventually is a root security of the wallet. So cryptography is always very complex and very hard to do it properly and secure. So that's also the reason why all of the thing, the crypto algorithm that we currently use, right, like TOS, SLL, or whatever, ISA, and so on, it takes a long way to be able to proven, right, to be secure. So I think that all of this going to be continue. I mean, because of all of these things very complex and is protect very critical. Nowadays, I think that in the Web3, all of the project is like $1 trillion, right, in the total market cap. So it's going to be continue. We will see that the issue will raise from time to time. Okay, so I think that we are out of time already. So thank you, and hopefully, I mean that today on the crypto part and math part is maybe boring because like different background, and you may not like get into the detail on how the whole thing works. But then eventually, that I think that we want to share on like the thing that normally we do in very detailed, very deep level of protocol, and chaining a number of different issues together to achieve, right, the end goal is like stealing money from the distributed open network. Thank you.
Thank you very much for Uyen and Thanh for a very insightful talk and along with the demonstration actually. So if anyone in our audience have questions, okay.
Thanks a lot for your talk. As we see, those blockchain technologies are very complex. And for me, it is very interesting. How do you explore the attack surface of those systems? It is not such easy like web security or application security. It's much more complex. How do you do that?
I think it's normal, right? I myself started security in 1995, so 30 years ago, right? So I also, along the way in my career path, I along the way go down into like hardware security as well as like over even like microcode and some lower layer of security. So I think that, and the team by itself, right? Why we actually the traditional security team that moving into Web3, with a lot of members going through like capture the flag. I think that if anyone here that been playing capture the flag for 15, 20 years, maybe know me as well, right? We run a big capture the flag team many years ago. Right, so the way that we approach is very simple, right? We look at the target that the most critical, right? And the more complex, that means definitely there will be something over there. Then we just go into approach like the way we play CTF, right? So understanding about the protocol, figure out where would be a potential attack area, and we look deep into that, right? And once we found an issue, then we're trying to figure out how actually you can achieve the end goal, right? So sometimes one vulnerability is not enough, then we need to find additional vulnerability. But we know exactly in order to be able to successful attack, then what type of vulnerability, additional, what type of vulnerability we need to figure out. Then we just, like narrow down the area that we need to look into. Then eventually we able to achieve that. I mean, of course, we need to have luck as well, right?
So can we say that the experience in other cybersecurity areas help in such complex targets, right?
Yeah, and also we have a very, very strong cryptography team, very strong security researcher team that work together. Normally, all of these will take us months to be able to figure out all of this. Yeah.
Thanks.
Thanks for the great presentation. And I'm also doing cryptography, so I learn a lot from the talk. But I have a very big question. Actually, this is not a technical question. I mean, in this kind of attack, as a security engineer, we cannot, if the attack happens, we cannot detect attack. We cannot respond to the attack. And we cannot even recover the actual vulnerability. As far as I know, there are a lot of vulnerability in this kind of zkEVM. So is that too early for us to adopt those zkEVM to the on-chain and to put so much money into it? Do you think it's too the progress is too rapid? And as far as we know, for many cryptography algorithms, you need disk to do the standard and to many kind of new things. But in recent years, maybe in past 5 years, there was a lot, implementation and new algorithm, all kind of new things in zk area. And yeah, so many money also going into it. But there must be many vulnerability. And how do we respond to those kind of things if real attack happens?
I would say, to be honest, right? So for let's say blockchain and on the chains, and when this serious attack happens, so there's a few different things that you can react. Like Ethereum in the early days, right? They just roll back, right?
Yeah.
A fork and roll back. So that's one way, right?
Because
actually,
but actually, if some maybe elite attacker, there are. As you mentioned in the slides, the attack is also zk, and they change the route, but they only change a little bit of the transaction. So you don't know the real attack happens. Maybe 1 year after the attack happens, you know the attack, but you cannot roll back all the transaction. How do we do it?
I think that I share it the same with you, right? So basically, on the whenever there's something that people does is a trend or revolution of a technology, let's say AI now or blockchain a few years ago, there's a lot of innovation and people trying to come up with different solutions to make it scalable, make it faster, make it whatever, right? And along with that, it's require a lot of different new technology or new protocol, right? And of course, the risk associated with that as well is because it's not proven, right? But I think that along the way, there should be standardized and make it become standard, and going through a lot of different peer review from both academic as well as the industry. The same thing that what we have done in the traditional industry as well. And along the way, it will become more mature and more secure. The only, I think the big part different is basically on traditional, right? When you get hacked, it doesn't mean that it's the end day, right? I mean, doesn't mean that you lose everything and you cannot recover and whatever. But on those kind of blockchain network, sometimes it's one thing is it's done, right? Very hard to recover unless you forget or you roll back the chains or something like that. I don't have the solution for that, to be honest. With my security background, I think that as long as you have invest enough, have good people, I don't think that any solution can be breakable. Can be breakable at some point. Even with the system right now that you think is secure, doesn't mean that after 1, 2, 5, 10 years still secure, right? So it's.
Yeah. Thank you for your answer. Yeah. Thank you.